Okay, taking off from this, we want to prove that this set is a basis of R3. Okay? What's a basis mean? Being a set is linearly independent and spans R3. Now, from the previous, for any vector x1, x2, x3 in R3, such that this combination equals x1, x2, x3. So the set spans R3. So we got this. Okay? So we can put in a check mark there. We got that done. Now all we have to do is prove that it's linearly independent. How to prove linearly independence? It says that the only linear combination of these vectors that equals a zero vector is the zero combination. C1 equals C2 equals C3 equals 0. IFF stands for if and only if. All the C's are 0. So what do we do? Well, we can write this equation by multiplying C1 by this, C2 by this, C3 by this. Same thing we did before. All the steps we did before. Write out what it means to multiply this, then what it means to add these, and then, okay, first element equals a first element, second element equals a second element, third element equals a third element, right? The same process we went through to get down to, well, we didn't get down to that, but that required the reduction, okay? Okay, so. The equation will then be equivalent to this matrix, right? Which reduces to the identity over here. And of course, no matter what you do These zeros are always going to give you 0. Okay? And this implies C1 equals C2 equals C3. That looks like a 3 equals 0, which is what we had to prove. There's a proof of linear independence. Okay? Now again, when you prove it, you want to write out all the steps for the time being. Give me something to spend hours reading. And make sure you understand all the connections. Okay, well, okay, so there it is. Okay, well, one consequence of linear independence is that none of these vectors can be written as a linear combination of the other two. Okay? So I want to go over to notation. I want to do this in general. And I want to say if the set is linearly independent, no vector in the set is a linear combination of the others. Okay? Uh-oh. And I'm saying that totally wrong. No, okay. So, I should use arrows in these because they're vectors. And when I type them, they're bold-faced, and we're used to that from your text, okay? Since the vectors are linearly independent, then the sum of multiples, this linear combination of all the vectors, can be 0 if and only if C1 and C2 and so forth, all the C coefficients are 0. Suppose Vn is a linear combination of the others. Okay? Then Vn, it'll be d1 v1 plus d2 v2 all the way up to dn minus 1 vn minus 1, not vn. Okay? For some constants, d1 through dn minus 1. Okay? in that case, this linear combination, dn v1 through dn minus 1 vn minus 1 minus vn would have to be the zero vector. So if C1 equals D1 up through Cn minus 1 equals Dn minus 1, and Cn equals negative 1, well, that's what we've got there. Okay? And that can't be so. It can't. That's the end of the proof.
Contradiction.
Oh yeah, it's a contradiction. It's a can't be so.
Yes.
Okay? Okay, use the formal language. Can't be so.
Okay.
Don't say contradiction.
Okay.
Yes, it's a contradiction. Now that's really what you want to say.
Yeah. Well, can't be so still gets the message across.
I.e., we got us a contradiction. Okay?
Okay. All right.
You're going to get a little emotional. You can't get emotional. This is a contradiction. Or this is a contradiction. This is a contradiction. No. Can't be so.
Okay.
You got to put a point on your proof.
Put some emphasis on it.
Huh?
Some emphasis on
Yes,
it.
yes. If you want to use polite words. Yeah, the I and can't needs to be capitalized. Sorry for the grammatical error.
Okay.